My name is Curly, student identification number A2076773. Today, I'm honored to present our research project for Stkm 2622 Advanced Chemical Analysis of Food. And the title of my presentation is Extraction and Characterization of Soluble Carbohydrates from Banana Passion Fruit Peel. This project focused on isolating functional polysaccharides from agriculture byproducts and validating them using advanced analytic instruments. To give you an overview of today's presentation, I will cover 6 core sections, and we will begin with the introduction and research rationale, followed by the systematic isolation and extraction process. Then we will dive deep into the core instrumental analysis, starting with the monosaccharides profiling via HPLC theory and moving on to the thermal characterization via DSC. Finally, I will provide a critical evaluation of its strengths, limitations, and industry synergy before wrapping up with our final conclusions. Let's begin with our research background. The biomass utilized in this study is the fruit peel of banana passion fruit. This peel is a juice processing byproduct rich in pectin, which this study extracts and characterizes. Pectin is a complex acidic heteropolysaccharide composed of alpha-1,4-linked galacturonic acid units with varying degrees of messy esterification. Valued for its gelling and stabilizing properties, converting this underutilized byproduct into a high-volume functional food hydrocolloid established an effective method for waste valorization that directly supports sustainable and circular economic principles. Moving on to the isolation and extraction process, the core extraction logic relies on a streamlined acidified water extraction followed by ethanol precipitation. The raw peel powder is mixed with dilute hydrochloric acid to adjust the pH strictly to 3.5, followed by hot water incubation at 80 degrees Celsius for 30 minutes. The acid microenvironment successfully hydrolyzed and solubilized the bond protopectin from the cell walls. The supernatant is then blended with 96% ethanol at a 1:1 volume ratio and stored at 4 degrees Celsius to induce precipitation. Crucially, this optimized workflow achieved an impressive final extraction yield of 23.2 plus or minus 0.05% on a dry weight basis. Furthermore, the degree of esterification was determined to be 76.93 plus or minus 1.65%. Because this volume is well above the fraction 50%. The extracted carbohydrates is classified as high maxopectin, making it ideal for rapid gelling applications. Next, let's discuss structure validation via high-performance liquid chromatography. For sample pretreatment, we apply gentle enzymatic hydrolysis using aspergillus niger pectin nails at 30 degrees Celsius for 2.5 hours to cleanly liberate constituent monosaccharides. For our instrument configuration, we utilize an Agilent 1260 infinity system equipped with a specialized high-plex edge cation exchange column measuring 7.7 by 300 millimeters. We selected a refractive index detector instead of a standard ultraviolet detector because carbohydrates lack ultraviolet chromophores and don't absorb ultraviolet light, making a refractive index detector absolutely essential for an accurate quantification. The separation was executed under a isocratic elution using 0.01 molar sulfuric acid as the mobile phase, maintaining a flow rate of 0.4 milliliters per minute, a column temperature of 55 degrees Celsius, and a total runtime of 25 minutes. As we can observe from our actual chromatography results presented in Figure 1, peak identification based on retention times reveal excellent structural details. A minor peak at 30.61 minutes corresponds to glucuronic acid reflecting trace impurities. Most importantly, the dominant peak appeared at 14.03 minutes, representing our target monomer glucuronic acid, minor neutral side chain sugars such as glucose, xylose, Rhamnose and arabinose were also detected with much lower intensities. Quantitatively, the total glycuronic acid content reached 65.4 plus or minus 2.24%. This high concentration satisfies international commercial purity standards and chemically confirms that our extract carbohydrates possess a highly pure homoglycerine structure backbone, confirming its identity as high-quality pectin. Now let's transition to the thermodynamic evaluation via DSC. Our analytical purpose is to systematically evaluate the material's thermotransition behaviors and the material response under controlled temperatures. To stimulate real-world industrial packaging applications, we utilize the lithoral plastic-sized pectin-based biodegradable films, ensuring our evaluation accurately reflects practical performance. For the core equipment, we use a high-precision TA instruments, DSC 2000 calorimeters. The thermal mapping was programmed from 5 degrees up to 3050 degrees Celsius at a uniform heating rate of 10 degrees Celsius per minute. The sample mass was kept between 5 to 6 milligrams, tightly sealed in perforated aluminum pans under a continuous nitrogen purge of 20 milliliters per minute to completely inhibit unwanted oxidative degradation reactions. Our DSC analysis mapped the thermal transition behavior aboard endothermic peak between 105 to 109 degrees, simply represents initial moisture evaporation from the evaporation of bond water molecules. Most importantly, a sharp and distinct exothermic peak is identified between 122 degrees, marking the primary structure degradation of the polymer matrix. This exothermic event represents the thermal cleavage of the alpha-1,4 glycosidic bonds in the pectin main chain, which initiates the irreversible breakdown of the polysaccharide structure. From a food engineer perspective, this established that our extract pectin remains completely stable with zero thermal degradation below 180 degrees, proving it's fully compatible with severe thermal processing operations, including pasteurization, hot filling lines, and industrial spray drying. Let us quickly evaluate our findings in the discussion section. Industrially, this extracted pectin inhibits robust functional potential as a thickener and gelling agent, proving to be a viable alternative to commercial citrus pectin. The key strength of this study lies in its green water-based isolation process that achieves a high 23.2% yield while advancing a sustainable circular economy. However, a notable limitation is that its raw purity remains marginally lower than highly refined commercial equivalents, and the enzymatic pretreatment required for chromatography is a destructive method. Crucially, the project highlights an advanced instrumental synergy. High-performance liquid chromatography acts as a microscopic chemical lens, revealing the precise monomeric identity of the pectin fractions. Conversely, DSC acts as a macroscopic physical lens, defining its thermodynamic boundaries. Together, they deliver a holistic structure-function evaluation. In conclusion, our research successfully proved 4 main points. First, banana passion fruit peel is confirmed as a valuable low-cost source for making high methoxypectin. Second, our acidified water extract and ethanol precipitation provides a simple and easy process. Third, HPLC and a refractive index detector showed a strong structure with 65.4% uronic acid. First, DSC results shows it's very stable against heat up to 220 degrees, making it easy to use in food production. Looking forward, this pectin is great for bakery products, hot drinks, and edible coatings to make food last longer. Thank you very much for your attention.